iterated integrals and area in the plane. In the previous chapters, we have discussed taking the derivatives, the concept of the derivative with respect to functions of several variables. Now we focus our attention on the integral in the same fashion. The integral calculus 1 of a single system or a single integral to now we can deal with double integrals or triple integrals and talk about what that means. Iterated integral simply means that we want to evaluate the integral with respect to limits of integration as the integral goes from some interval a to b, for example. And we talk about the area that's contained within a region of a plane. So let's begin. So first, the area of a plane region. A region has to be bounded everywhere, bounded on its left and right side, and bounded above and bounded below. And so the region is contained. So we call capital R a region. R is called a region. And from that region, we want to be able to build the so-called double integral to calculate the area. The region is found by the containment of vertical lines, here vertical lines A and B, or it could be horizontal lines C and D. So we say that the system is said to be vertically simple if we have vertical lines bounding the region, x equal a, x equal b, and then a function below g sub 1 and a function above g sub 2, where the region is said to be contained. Or we have what's called horizontally simple if the region is contained by horizontal lines, y equal to c, y equal to d, and then a function h sub 1 on the left and a function h sub 2 on the right. And so the area is strictly written for the vertically simple as the integral from a to b times the integral from g sub 1 of x to g sub 2 of x dy dx. We make the notation dy dx because of the vertically simple region, the region that's bounded by two vertical lines. So the integration of dx goes on the outside. Or if it's horizontally simple, the double integral is the integral from c to d, and then the integral, it's not times, I said that back here, please excuse me, it's not this integral times that integral. It's the integral from c to d, and then also the integral from h sub 1 of y to h sub 2 of y, dx dy. If it's horizontally simple, then everything must be defined in terms of y. If it's vertically simple, then the limits and the notations of the variables must be defined in terms of x. So we give the definition for the area of a region in a plane if it's vertically simple or if it's horizontally simple. R is defined for vertically simple where x is bounded by two vertical lines, x equal a, x equal b. Y is contained by two functions below and above, g sub 1 and g sub 2. The functions g are continuous on the closed interval ab, then the area is defined here strictly. And then the same argument for horizontally simple. Now my notation is this: to integrate a double integral with respect to dx dy or dy dx, we want to use the following. If it's vertically simple region, dy dx, you first integrate with respect to y, and you're gonna hold x as a constant, and then evaluate with respect to y, and then thirdly or lastly integrate with respect to x. If it's horizontally simple region, first integrate with respect to x and hold y as a constant, and then evaluate with respect to the x terms, and then lastly integrate with respect to y. Let's look at some problems, straightforward problems, see if we could work through this. So here I'm going to integrate first with respect to y because it's dy. And then secondly, we integrate after that, the evaluations, we integrate with respect to x. So first integrate with respect to y. So this is x, we treat x as a constant. So this is x times y plus 1/2 y squared. Y is evaluated from 0 to 2. And then this is dx. So this gives us the integral from 0 to 1. We evaluating the y. So this is 2x plus 4 divided by 2 is a 2 times here dx. Now we integrate, it's a single integral, calculus 1, integrate with respect to x, so this gives us x squared plus 2x evaluated from 0 to 1, so we get 1 plus 2 is 3. Well, integrate with respect, and I keep forgetting to put my trash can out here for the young lady. Excuse me, and I think sometimes breaking up the monotony is a good thing. So. Okay, I'm back. Integrate this first with respect to x because the dx comes first, right? So this is the integral from 1 to 2. Integrate with respect to x, we get 1/3 x to the third minus 2 y squared times x. Evaluate the x from 0 to 4. And so this is, better go this way just to be on the safe side, the integral from 1 to 2. This is x to the fourth, so that's 64 divided by 3 minus 2 times x evaluated at 4 is 2 times 4 is 8 y squared and this is dy. Now we integrate with respect to y, so this is 64 over 3 times y minus 8/3 times y to the third. Here the y is evaluated from 1 to 2. So we plug in y to be 2, so that gives us 128 over 3. This is minus 8/3 times 2 to the third, that's 8 times 8 is 64 all over 3. Now we evaluate the y's at 1, so this becomes minus 64 over 3. 64 over 3 times 1, evaluated here with this minus sign. And then this is minus a minus, that's plus 8/3 times 1. I kid you not, that was supposed to be a 3. Okay. So now, what about this one? We first evaluate with respect to y. So this becomes the integral of 1 dy is y. This is plus, we treat x as a constant, so this becomes y times this cosine x. Now the y's being evaluated from 0 to sine x dx. Right? So again, y is evaluated from 0 to sine x. This is the integral from 0 to pi. And so we evaluate this y at sine x, so we just get sine x plus this y evaluated at sine x. So this is sine x cosine x. Then we evaluate at 0, we get 0. So this is dx now. So you integrate sine x, we get negative cosine x. Here we use a u du substitution. So you let u equal to the sine x, and du picks up the cosine. So when you integrate that, we get the integral of u, which is u squared divided by 2, so plus u squared over 2. And so this is negative cosine x plus sine squared x over 2, evaluated from 0 to pi. So we plug in cosine x at pi, so this is negative cosine pi plus sine squared of pi over 2. Then this is minus, this minus is plus cosine of 0 minus sine squared of 0 over 2. Well, cosine of pi is negative 1 times this negative is positive 1 plus sine of pi is 0, and then plus cosine of 0 is 1, and then minus 0. So we get 2 for our answer. What about this one? So integrate here, this is integral from 0 to 1. Integrate with respect to y, that's good for us, so it makes it easy. So this is just y. Y is being evaluated from 0 to x, and it was times that 1 minus x squared dx. So evaluate the y at x, so we just get the integral from 0 to 1. This is x times the square root of 1 minus x squared dx. So now we use the u du substitution. Let u equal to 1 minus x squared. So du is negative 2x dx. That is negative 1/2 du can pick up for us that x dx. So we have the integral, it's negative 1/2 in the front because it is negative 1/2 du to represent the x dx. And this is u to the 1/2 du. So we get negative 1/2 times u to the 1/2 plus 1, 3/2 divided by 3/2, and this is evaluated from 0 to 1 with respect to x, not the u. So we have to clean this up by all means. So the 2 goes upstairs, 2 divided by that 2 goes out. So we have left just a negative 1/3. And this is u, which u is the 1 minus x squared. This is raised to the 3/2 power, evaluated from 0 to 1. So we plug in x equal to 1, we get 1 minus 1, that's 0. Then this becomes minus this minus, so we get 1/3 times 1 minus 0 to the 3/2 power, and that just gives us 1/3 for our answer. Okay. Well, let's keep moving. So we integrate this guy first with respect to x. That's good for us because you have these y's here. They end up being very hard. So this becomes the integral from 0 to 2, and this is x times, and let me clean this up. Yeah. So this is x evaluated from 0 to the square root of 4 minus y squared, and then this is times 2 over the square root of 4 minus y squared. Then over here we have dy that we haven't gotten to yet because we have to do the evaluation. And I pulled these terms out because I'm not evaluating those guys. We're evaluating with respect to x because we integrate first with respect to x. This is dx dy. So this is the integral from 0 to 2. We evaluate this x at the square root of 4 minus y squared. And then this is times 2 all over the square root of 4 minus y squared. So you see that these radicals cancel. So you have left the integral from 0 to 2, just 2 dy. We wish all of life was that simple. Tell you what, it does become, life philosophically has a neat way of working through it when, one, you know the foundational principles of which to use so that you can cancel out some things in life, of which what is left is some type of integration that is some kind of combination, juxtapositioning of things to make what I would call in art a beautiful tapestry, where there's a family with children, a job where the people work together in a cohesive manner, the military, of which you see that, um, a country, a nation. We have trouble with that, as you can see, even with our own government and other governments, and how governments tend to break down because people don't integrate that well. We ought to require maybe everybody to take calculus and understand the philosophical principle behind computing and evaluating integrals. What does that mean? That somehow things that are said to be different at times can get along. Well, enough philosophy for today. Integrate this 2 dy, and that gives us 2y. Y is evaluated from 0 to 2, and here we just get 4. Now, let's look at a couple more problems. In exercise blah 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 to blah blah blah, sketch the region R whose area is given by the iterated integral. Then switch the order of integration and show that both orders yield the same area. That is supposed to be the case. Well, let's draw this out to see what we have, and to write the region. This region says this. I never could make those. That's a little bit better. Here, y is bounded from 0 to 2, x is bounded from 0 to 1. You get that? This inside integral goes with this differential dy, and then the outside integral goes with this outside differential. So x is bounded from 0 to 1, and then y is bounded from 0 to 2. All right. So what is that? Well, we graph just based on what we have here. So x goes from 0 to 1, and then y goes from 0 to 2. I need some help because of my hand being crooked, I guess. So this is the region. So you integrate. Obviously, this is a rectangle, so the area, whether it's arithmetic, algebra, geometry, or calculus, we get the same thing. So the area is the length times the width, so we ought to get 2. So over here we have the integral from 0 to 1. We'll integrate from 0 to 2. This integral dy, that's y evaluated from 0 to 2 dx. So it just gives us 2 times the integral from 0 to 1 dx. So that gives us 2x evaluated from 0 to 1. That's just 2. Well, if you switch the order of integration, do we get the same thing? Yes, we do. Now here's the thing. You can switch this order of integration and work it out directly. Nothing typically changes because this is a fixed region. It's a rectangle. There's no curves where you get different values as you move, from different places. Here it's static, so we can switch this around. Integrate from 0 to 2, integrate from 0 to 1. We switch the order of integration. This is dx, dy. It's the integral from 0 to 2. X is evaluated from 0 to 1, dy. So we just get 1 times the integral from 0 to 2, dy. That gives us 2. Y evaluated from 0 to 2, which is 2. Now, this is the way you switch the order of integration from 53 seems to be very easy. Don't assume that it's going to be like that always. Typically, it's not. Let's see. So this region here is defined. X goes between these two uh, sectors of a circle. So a quad sector. So here we have negative square root of 1 minus y squared is less than or equal to x, less than or equal to the square root of 1 minus y squared. And then y goes from 0 to 1. Well, let's see how that looks graphically. So y goes from 0 to 1, and then x to the left has this part of the circle. It does that, and then x on its right side, we get that side of the circle. So on this side, this is here x being represented by the square root of 1 minus y squared. And then on this side, x equal to negative square root of 1 minus y squared. And this is 1. Right? So y goes from 0 to 1. Let's integrate this. So we have the integral from 0 to 1. We integrate here dx, we just get x as evaluated from negative square root of 1 minus y squared to the square root of 1 minus y squared. This is dy. So this gives us the integral from 0 to 1. We evaluate the top one. This is the square root of 1 minus y squared. Minus, this minus becomes plus the square root of 1 minus y squared. dx. So this is 2 times the integral from 0 to 1 of the square root of 1 minus y squared. I don't know why I changed that from dy. It is dy on the outside to dx, supposed to be dy. Thank you. Did you catch that? I think I could almost hear you. Somebody else was like, I don't know what happened. Well, don't feel bad. I just made a mistake. So this is dy. I knew something was wrong because here this radical was in terms of y, but I had a dx over there, which, I mean, you could integrate that, but I knew that something was fishy. Well, we can use a couple of things here. You can use a table to integrate this, but if you're on a test, you don't have the access of a table. That is if you're taking the test fairly. We do it by hand. We use trig substitution. So you recall this is of the form here, let sine theta equal to y over 1. And this side would have to be 1 minus y squared. So if that's the case, I need this square root. Well, that's the cosine. So cosine theta is the square root divided by 1. So that's just the square root of 1 minus y squared. Now I come and I consider the sine theta equal to y implies, take the derivative of both sides, we get cosine theta, use the chain rule, d theta, the derivative of theta, is equal to dy. So what do we have? Got this guy right here. I need to go here. This is 2 times the integral from 0 to 1. I'm going to represent this square root, that's cosine theta, and then represent the dy. Represent two things, right? The dy is this cosine theta d theta. Cosine theta d theta. And later on in life, or later on in this course, we will look at an easier way to deal with this. This is 2 times the integral. Somebody was trying to call me, whoever that was. It wasn't my wife, or the kids, or mama, or my mother-in-law, or my father-in-law, or my brother, or my sister. So, let's take this guy and put it here. This is 2 times the integral from 0 to 1. 0 to 1. Cosine square d theta. Theta d theta. We use something from trig, a trig identity, to help us, and this goes right back to a section in Chapter 8 of Calculus 2. So this is 2 times the integral, but the identity comes from trigonometry. So this is 1 plus cosine 2 theta all over 2 d theta. Well, 2 cancel out with that 2, so it's the integral from 0 to 1 of 1 plus cosine 2 theta d theta. So integrate the 1 d theta, that's theta. Integrate this cosine, right? And remember, you have to use a du here, u du, let u equal to 2 theta. Du is 2 d theta, so we get a 1/2. So this is plus a 1/2. The integral of cosine is sine. This is 2 theta. Evaluated from 0 to 1, of which we cannot get to because the 0 and the 1s were with respect to x and y, not theta, right? So this is theta plus sine 2 theta is 2 times cosine theta times sine theta, right? So this is 1/2 times 2 times cosine theta times sine theta, another identity from trigonometry. This is theta plus cosine theta times sine theta. Why am I doing plus? Tell you what, I'm getting hungry, I know that. So cosine theta, you recall, is that square root, and then the sine theta is y. So here we have theta plus cosine theta is the square root, and then the sine theta is y. So this is y times the square root of 1 minus y squared. Now, what's theta? Well, you go back to this let statement. That's most important. So if sine theta is equal to y, then we take the inverse of both sides. Then sine inverse of sine theta is equal to sine inverse of y. Well, sine inverse of sine theta is just theta, right? This implies that theta is equal to sine inverse of y. So this is sine inverse of y plus y times the square root of 1 minus y squared. Now we can do the evaluation. So we evaluate that. We get sine inverse of 1 plus, we plug it in, y to equal to 1. So this is 1 times 0 minus sine inverse of 0 minus 0. Now sine inverse of 1, sine of what gives us 1? That's pi over 2. And then this is 0. And then sine of what gives us 0? Just 0. We get pi over 2. Now, does that make sense for the answer? Let's come back. Yeah. This is half of a circle. We know that if it's the area of a circle is pi r squared. Here the radius is 1, right? So the radius is 1, but this is not the whole circle, it's half of a circle. So this is the area for the semicircle. So pi r squared over 2. So if that be the case, you get the area is pi times 1 all over 2. That makes sense. Now, let's go back and look at the question. Then it says, then switch the order of integration so that both sides yield the same area. So we got to switch this and then integrate that. So the region is the same graph, right? The same half circle. But now x goes from, this was, 0 to 1. X goes from 0 to 1. Excuse me, x goes from -1 to 1. Just look at that, right? So our region, x goes from -1 to 1. What about y? Y goes from 0 got to be able to get that curve in there, right? Well, that's just the equation for the circle in terms of x, the square root of 1 minus x squared. So now we find the area based on this region. So x goes from -1 to 1, and then y goes from 0 to the square root of 1 minus x squared. So this is dy dx. We look at one vertically simple, look at one horizontally simple, and want to make sure by switching the order of integration we get the same result. See how you switch this order of integration and the terms are different for the limits of integration in comparison to this guy right here, right? This was dx dy. So just saying I'm going to change this from dx dy to dy dx, just can't flip-flop these guys. Can't do that here. Now, could do it with a square or a rectangle, right? But that's about all you can do it with. So this is the integral from -1 to 1. Integrate with respect to y. This is y evaluated from 0 to the square root. So this just becomes the square root of 1 minus x squared. This is dx. We use our trig substitution on this. I'll go through this one quickly. You get the idea from before. The hardest part, I think, is on the evaluation at the very last end. So let's sine theta equal to x over 1. We get that square root of 1 minus x squared there. From here we get cosine theta d theta is dx. And then from the triangle, cosine theta is the square root divided by 1. So we can write this integral from -1 to 1. The square root is the cosine, and then the dx is the cosine theta d theta. So this is cosine squared theta d theta. Similar to before. Remember before it was 2 times the integral, but it was from 0 to 1. See that? Just cut it in half. So we took my sins and he put them in a bag. That's the book of Job. Job said he took my transgressions and he sealed them in a bag. Job chapter 14. Anyway, this guy. So this is the integral from -1 to 1. That cosine squared can be written as 1 plus cosine 2 theta all over 2. d theta. We integrate. We get 1/2 theta. This is plus. You got a half sitting down there, but you have to use u du substitution on that 2 theta. So you get a half there. So that's 1/2 times this half is 1/4 times sine of 2 theta. The x is evaluated from -1 to 1, not the theta, so we have to transfer. So this is 1/2 theta plus 1/2 cosine theta sine theta. You write that sine 2 theta use sine 2 theta, that equals 2 cosine theta sine theta, right? So the theta, you know, this is 1/2. This is going to be the sine inverse of x now, right? Because it's with respect to x. And then this is plus 1/2. The cosine is the square root. And then the sine theta is x. So this is x times the square root of 1 minus x squared. Evaluate that from -1 to 1. So we get 1/2 sine inverse of 1 plus, you plug in x equal to 1, you get 0. This is minus 1/2 sine inverse of -1. And then minus, you plug in x equal -1, you get 0 over there as well. So, so when is sine 1? Well, sine of what gives you 1? That's power over 2. So this is 1/2 times power over 2 minus 1/2. And when sine of what gives you -1? Was that 3 power over 2? So we get power over 4. This is minus 3 pi over 4. And it's supposed to be positive power over 2. Huh! Tell you, not when I'm hungry. Gives us power over 4. I've lost the negative sign somewhere. Makes me very sick. I was looking at my paper. I don't even see how I got the stupid negative there. Right? Don't nobody knock on my door. I do not want to be bothered right now. What sense does this make? Is this even possible? Oh, that's very weird. Okay, this is power over 4. I had negative here on my paper. Makes no sense. Let me take a break and let me eat my lunch and come back and try to fix this. It's supposed to come out with power over 2, and this is negative power over 2. It's supposed to be a negative somewhere up here, of which all the signs would alternate, and this would be negative and that'll be positive, and then we'll all be happy. But how did I get the negative here? I do not see it, because this was the 1/2 theta. You integrated cosine, you got just sine. I'll come back and try to fix that.